Okay, we ended here, so we are going to continue with the various protection design and the various protection schemes. So for the design criteria for protective system, the protective system should be reliable in the sense that it should function properly in terms of dependability and security. So we must depend on the system that it should react correctly, appropriately, and also avoid unnecessary operations as an aspect of security. Then the selectivity here has to do with the protective scheme being able to recognize a fault, yeah, and trip with a minimum number of circuit breakers, or yeah, to clear the fault. So that's the aspect of selectivity. Then speed has to do with the time of response. The protection scheme or protection system should not be too slow to react or too fast to react. If it's very slow to react, some of the faults might cause potential damage on the line or the equipment. And also there are some faults that just come temporarily and are just being cleared very fast. Yeah, and if the system is too much fast to react to those kind of faults, it might produce some unnecessary response. You might see that the network might just be reacting or isolating part of the network every moment, every time. Meanwhile, those faults were not really potential faults that could create serious damages or that could create damages to the system. Might be just some small transients which are cleared instantly. So the potential scheme should be able to recognize this. So recognizing it as well is the aspect of this selectivity. Yeah, but now the speed has to do with not being too fast or too slow to react. So it should be average. Then simplicity here has to do with using a minimum number of equipments to provide a very simple and simple circuitry in order to protect the system, and as well economical if it is very much at a lesser cost in designing that protection scheme or operating the protection scheme. It is very good. So these are the various protection design criterias which a protection scheme should have. Then looking now at the basic line protection technologies, this is just an overview. We can see maybe line classification according to voltages. For transmission lines, we have voltages of 132 kilovolt and higher, and that's normally primary transmission. Secondary transmission from lesser than now 132 kilovolt to 33 kilovolt. Then lesser from 33 kilovolt lesser, we have distribution. That's distribution. So, and we also have voltage level classification, what we call the high voltage, the extra high voltage, the ultra high voltage, medium voltage, and so on. Then our focus today is on these protection schemes. Yeah, we have these four protection schemes that are mainly used: overcurrent protection scheme, directional overcurrent protection scheme, distance differential protection, and also pilot. So we have seen the various types of relays, and those relays are used now in these protection schemes in order to provide appropriate uh, protection of the system. So generally, this is how the protection scheme is. If we wish to indicate all the protection devices, the circuit breakers, the control, the voltage transformer, the current transformer, the relay, yeah, how they are used in protecting the line. So this is like a general overview. So we have normally the circuit breaker doesn't operate alone. It operates based on what? Based on a control signal that has been given by the relay to the circuit breaker to trip in case there is a fault or not. So it is the relay that is able to know whether there is a fault or not, and is able to know if there is a fault or not based on what? The readings it have from the current transformer, that is the current readings, and the voltage readings from the voltage transformer. So with this, it's able to identify whether there is a fault or not before giving a tripping command to the circuit breaker. So that tripping command here is simply by closing some of the relay contacts, of which when the relay contact closes, it causes what, this small DC battery to supply the trip coil of the circuit breaker, which causes the line to trip, which energizes and causes the contact of the circuit breaker to open, thereby tripping the line. Here is still the same thing, the same illustration of how those various equipments can be interconnected in order to provide the protection uh, uh, control action. Okay, so what is very another thing which is very much essential to understand or to know in power system protections are the zones of protections. What are zones of protections? Zones of protection are simply zones in which if there is a fault within that protective zone, the circuit breakers operate within that protecting zone operates. So a power system network can be divided into several protective zones, right? So if there is a fault in one protective zone, the relays and the circuit breaker in that protective zones are the ones to operate. So you need to know how to establish a protective zone, and there are various criteria in establishing a protective zone. Protective zones are established in the sense that every equipment normally should fall under a protective zone, and also the protective zone should overlap, right? That means it should have an overlapping. We are going to see down, we're going to see much of this down. Then we have what we call backup protection and primary protection and backup protection. So primary protection is simply the protection in the sense that the circuit breakers within the zone of protection react in case there is a fault within that zone. Then for backup protection, it is simply if the primary protection fails, the backup protection takes off over, and the backup protection are not necessarily within that the primary zone of protection, right? That's what we call them, backup. So we'll see that, for example, in we'll see that, for example, in this figure, how zones of protection can be established. So you see the generator here. The generator here should be protected by a relay. This is a relay. The relays are indicated here in these small square boxes. So each equipment, the various equipments should be protected by a circuit breaker. For example, you see the generator at this end, another generator at this end with a transformer. So at this end, we can protect this equipment at this end with a relay so that it falls under one zone of protection. Then you see now also the bus. The conditions for a bus is that you must have a protective relay before and after a bus. So that's why we see on this line there is a relay before the bus and after the bus. So you see also on this other line there is a relay before the bus and after the bus. Since it is the same bus, all those four relays fall under the same zone of protection. This is zone of protection here indicated here, right? And you see that when you draw that, it is overlapping with this one, and this zone are overlapping. This other zone with this zone of the bus are overlapping. So that's what I was trying to describe above. Then you see now this transformer. This transformer now should be protected as well. Since this relay is already there, which is protecting the bus, right? You as well be protecting this transformer, so that in case there is a fault leaving from this bus, it should not come and affect this transformer, right? And if there's a fault at level of transformer, it should not cause to affect the bus. So this relay stands to protect against that. And also another relay is supposed to be included here in the sense that if there's a fault in the transformer, it should not lead to this other bus. So you see how you can put relays in order to draw, come out or to draw the protective zones. And so you see the protective zone of this transformer now here will be this line. See all those two relays fall within that protective zone, and you see that it interacts with what, this zone and this other zone. So you can do that for the whole of this power network, right? You see, for example, this line probably ends or is going to somewhere else. So you have this relay here that is used to protect this line. That's another zone of protection. So this is how you can draw zones of protections in power system. And in case if there's a fault within a zone of protection, that circuit breaker within that zone act. For example, let's say if there's a fault at the level of if there's a fault F1 at the level of this line, if there's this fault F1 occurs at the level of this line, the circuit breakers that should act are the primary. So this is what we call the primary zone. This is what we call primary protection. The circuit breakers that should act is circuit breaker B8 here and B10, right? In order to clear or isolate this fault, not to affect the power system network. So that's the primary zone of protection. So the backup protection entails that what if the primary protections fails, that means B8 fails to act, then the next release in the in the next zone, right, should react. In the next zone which overlaps with it should react. So you see here, if B8 fails, B5 and B7 should react, right? And if B10 also fails, B12 here will react. Not only B12, B11 and B13 because they are connected to what? The same bus. You understand? Okay, so that's the secondary zones or secondary protection. So you can be asked, right? What is a primary protection circuit breakers or relays, and what is the secondary protection circuit breakers? So these are the circuit breakers for secondary protection. You have B11, B12, B13 because they are connected on the same bus for a fault at F1. Also, we have B5 and B7. They react for the fault at uh, uh, F1 in case it fails. So we also have that of fault at F2. You can look at that one as well. So I believe you now understand what zones of protection means in power system. Then we now look at the first protection scheme, which is the overcurrent relay protection scheme. So here we use an overcurrent a current transformer only. We don't use the voltage transformer, but only the current transformer. So the current transformer is used because we need the value of the currents on the line. So when the current transformer is used, the current produced is fed what to this relay. This is the relay, and the relay is able to know whether that is a faulty current or not. If it's a faulty current, closes its contacts, thereby permitting this DC voltage to energize this coil and causes the contacts of circuit breaker to trip. It's the same schematic that occurs. It's the same schematic here. Okay, so that's simply how an overcurrent relay operates, and it's mostly used in radial systems or radial lines because we have different lines. I think well, we have seen that, right? The radial system network, the ring, and the mesh or interconnected system network. So this is an example of radial line overcurrent protection scheme. For example, we have three buses here, right? Uh, uh, bus 3, bus 2, and bus 1. Okay, let's consider the various substations. Substation A, substation B, substation C. So with respect to that, we have the relay and circuit breakers that protect that particular bus or substation there. These are the various relays and circuit breakers. Okay, so that's a simple overcurrent relay protection scheme for that radial line. Then there's what we call relay coordination. So relay coordination here, or coordination time, coordination delay time, which is normally referred as CDT. You can see it here. It's a time interval that is necessary between two adjacent relays, right, to react. Okay, let's say for example, we have a fault at this bus C, right? Okay, beyond bus C even. circuit breaker CB1 is supposed to react. What if circuit breaker CB1 fails to react? CB2 is supposed to react, right? But now there's a time required for this circuit breaker 2 to react. So that's what we call that coordination time. Hmm? Same thing if this circuit breaker 2 fails as well. Circuit breaker 3 should react, but within a particular point in time. So that time here can be represented on this curve as such. Mm. So we have this time of relay for the various substation 3, substation 2, substation 1. And we can see that, for example, if the circuit breaker 2 is to react, then the coordination time here should be the operating time for circuit breaker 1 plus the error margin. That error margin entails might be other criteria that probably add up to give some small time, which wasn't really the time required for the circuit breaker to react. So that's an error margin, right? Like in every system, you always have a small error. It has been illustrated here, up here, that most of the times you would take the error margin to be 0.3 seconds. Probably might be errors due to might be calculation, delay, or you have other criteria due to might be the errors due to relay or current transformer tolerances and so on and so forth, or energization and disenergization of release and so forth, and so you have to consider those error margins. So if the error margin is not giving you 0.3 seconds, then what if it's the circuit breaker 3 that is to react? Then you normally have the time for circuit breaker, the operating time for circuit breaker 2 plus what? The coordination time. That coordination time now should be that probably is that 0.3 or if it's specified. Yeah. Then we have some few examples